Our first speaker is Jonathan Boretsky from Harvard University, who's going to tell us about the non-negative complete flag variety and its tropicalization. All right, take it away.
All right, let me just get my screen shared. Okay. Yeah, hi, my name is Jonathan. I'm going to be talking, as Marud said, about the non-negative complete flag variety and its tropicalization. And also this title slide is going to serve as a sort of roadmap what I want to talk about. I'm going to tell you what exactly the non-negative complete flag variety is. I'm going to tell you a little bit about what it means to tropicalize a variety, and then I'm going to comment something about the tropicalization of this non-negative complete flag variety. So let's start with non-negative complete flag variety. And before we get there, let's actually start with just the complete flag variety without the non-negative adjective. So complete flag is going to be a collection of subspaces, V naught contained in V1 all the way up to Vn. Notice I have n subspaces and the inclusions are strict. So this means that actually the dimension of the ith subspace has to be I. And one way to think about these is as coming from full rank real matrices. And the correspondence here is that the ith subspace is going to be the span of the first I rows. So these are strictly contained in one another. And because the matrix is full rank, the ith subspace will in fact be of dimension I. And if we have a matrix like this, we can look at its Plicker coordinates, which are defined by taking any subset I of numbers from 1 to n. And then the Plicker coordinate indexed by that set I is going to be the determinant of the submatrix, which is in rows 1 through the size of that subset, and then the columns actually indexed by that subset. So for example, well, here's the definition again. And for an example, here's a matrix, which is full rank. The Plicker coordinate P1 is just 1. It's telling us to look in the first row and the first column. First row because the size of the index is 1, and first column because the index itself is 1. P2 is 2, so the size of the index is 1, and it's the second row column because it's 2. P3 is going to be 1. So I guess more interestingly, P12 is telling us to look in the first 2 rows and the first 2 columns and to take the determinant of the submatrix here, 3 minus 2 is 1. P13 is telling us to look at the first 2 rows because it's a size 2 index, and then the first column and the third column. So the determinant of this matrix is 1 times 4 minus 1 times 1 is 3. P23, the determinant of this matrix is 5, and then P123, the determinant of the whole thing is 4. So these are the Plicker coordinates of this matrix. Okay, and we can define this, but are these actually interesting to look at? And the answer is that yes, the Plicker coordinates are interesting to look at. In fact, they uniquely determine a flag up to some rescaling of coordinates which have the index of some fixed size. And the reason for that is if I scale a row of this matrix, it doesn't actually change these row spans here. It doesn't matter if I multiply a row by something, but it's going to change these determinants by some constant factor, and that's okay. But up to that ambiguity, these each determine a flag. But not just any vector of length 2 to the n minus 1 can actually be the Plicker coordinates of a flag. There's some rules, there's some relations between them. And the set of vectors which do represent Plicker coordinates form a variety, which we call the complete flag variety. And these are cut out by a set of equations, which are called the instant Plicker relations. And those relations are just exactly like the minimal relations you'd expect between the topmost minors of a matrix, because I mean, that's essentially what they are. Okay, so that's what a complete flag variety. Now let's add in the non-negative part. And the non-negative part of the complete flag variety comes from work of Lustig, but his definition requires quite a bit of work. So instead, I'm going to assert that the non-negative part of the complete flag variety is just those points in the complete flag variety with non-negative Plicker coordinates. So this is special to the complete flag variety. You can imagine a partial flag variety where maybe you don't have all n vector spaces, linear subspaces. You might have like skip a step there. And then the obvious analog of this theorem fails, this lemma fails. But for the complete flag variety, at least it's nice enough to describe it this way, and certainly simpler than actually following what Lustig does. So we'll stick with this. And it's known that this space, the non-negative complete flag variety, has a decomposition which is indexed by pairs of permutation v less than or equal to w in the Bruja order. And this is due to Marsh and Reach, who gave this parameterization, this decomposition. For those who do not know what the Bruja order is, for now, it's some partial order on the permutations, and I will give you the key quality of it when I actually use it on the next slide. And what I'm going to do is I'm going to show by example a way to parameterize one of the pieces of this decomposition for some given pair v less than or equal to w. And before I get to that, I just need one piece of notation. I'm going to let Si be the transposition I plus 1. So it's the permutation swapping I and I plus 1, the simple transposition. So here is my example. I'm going to work with W, which I'm going to write as a product of these simple transpositions, S1, S3, S2, S1, and V is going to be S2. And this is less than or equal to W in the Bruja order, which just means that I can find V sitting within S1. So I colored it in red. Sorry, within W. So I colored it in red in W. You'll notice that I wrote these in a reduced way. This is the fewest number of transpositions I can use to write out W. And of course, for V, it's the fewest number of transpositions I can use. There's some more technical playing around to write them out like the right way. I'm going to drop the word positive subexpression, positive distinguished subexpression, if that means anything to anybody, but it's not like arbitrary the way I wrote this, but that's some technical detail. But here's what we do. We start with this directed graph. We have the numbers 1 through 4 up the left side and the numbers 1 prime through 4 prime across the top. And then we go through the word W, and for each black letter, SI, we add in a weighted vertical edge from the ith strand from the bottom. So we start with an S1, and we add in a vertical edge from strand 1 to strand 2 from the bottom. Okay, the next letter is S3, so we do the same thing. We add a weighted edge from the third strand up to the fourth strand from the bottom. The red letters are a bit more complicated. So for a red letter SI, what we're going to do is we're going to switch two of the strands. When we switch these strands, we're going to switch the unprimed vertices, but we're not going to switch the primed vertices, and we're going to hold on to any incidences. So here's a before and after. I have an S2, so I'm swapping the second and the third strand, and with them, the unprimed numbers at the edges here. So this becomes 3, 2 instead of 2, 3. I don't touch the unprimed vertices. Sorry, I don't touch the primed vertices. And my arrows, my vertical edges maintain their incidences. So this was incident to the third strand. Now it's incident to the second strand, the arrow labeled B. And similarly for the arrow labeled A, it was incident to the second strand. Now it's incident to the third strand. Okay, and then there's one more letter to go. It's an S1. So I add a vertical edge from the first strand up to the second strand. I have no more room in the first column, so I just move to the next column. I can't have a vertical edge like below another vertical edge. Okay, and I said this is going to be a parameterization of a piece of the non-negative complete flag variety. But I said the non-negative complete flag variety comes from matrices, so somehow I have to turn this graph into a matrix. And here is the construction for that. I'm going to come up with the matrix M, where Mij, the ijth entry, is up to sign the sum of the weights of all paths from I to j prime. And when I say the weight of a path, I mean you're going to follow the path and you're just going to multiply any weights you find along the way. So for example, the 1, 2 entry, I look at all my paths to go from 1 to 2 prime. In this case, there's only one path. It's the path that looks like this. It's the only way to get from 1 to 2 prime. And I look at the weight here. The only vertical edge I pass is C, so my weight is C, and that's why I get a C down here. And then there's some sign consideration. So for the entry 3, 2, there's only one path from 3, 2 prime. It's a diagonal path, so it doesn't use any vertical edges. So there's no weights, so it's just 1, but I put a minus because I need that to make everything positive. And there's some obviously algorithmic way to do that, but that's another detail which I don't think is all that interesting here. Okay, but now I want to change stories to tropicalization. So again, I'm going to kind of define things by example. Here's a polynomial, x squared minus 3xy plus y squared. And we're going to talk about the tropicalization of P. And the way we get that is we switch multiplication for addition, and we're going to switch addition / subtraction for minimization. So in this case, my x squared, which is x times x, becomes x plus x, or 2x. 3 times x times y becomes 3 plus x plus y, and y squared, y times y, becomes y plus y, which is 2y. Okay, and these minuses and pluses just tell me to take the minimum over these three terms. So for now, I'm treating addition and subtraction on equal footing. So you might ask why I put a subtraction in this example in the first place. We'll get back to that in a second. But what's a solution to a tropical polynomial? That's going to be a point where the minimum value in this like minimization here occurs at least twice. So in our case, we're saying either the first two terms are equal and less than or equal to the third thing. So 2x equals 3 plus x plus y less than or equal to 2y. Or some other permutation that you have 2x equals 2y less than or equal to 3 plus x plus y, or the last option is 2y equals 3 plus x plus y less than or equal to 2x. On the other hand, a positive solution to a tropical polynomial requires not only that this minimum occurs twice, so it's kind of a stricter condition, but one of those terms, such as a minimizer, has to come from something in the original polynomial with a plus sign, and something has to come from a term with a minus sign. So in this case, we have two positive terms, x squared and y squared, and one negative term, 3xy. So we're asserting that the 3 plus x plus y has to be part of our minimum. So either 2x equals 3x plus y less than or equal to 2y, or the same thing with x and y reversed. So for example, the point 0, 0 is a tropical solution to P. This equation holds 2 times 0 is equal to 2 times 0 is less than 3. But it's not a positive solution because it's easy to see that neither of these things hold. Okay, so this is a tropical solution to a polynomial. And given some collection of polynomials, we can define the tropical variety of that collection of polynomials to be just the collection of common tropical solutions to all of those polynomials. And we can define the non-negative part of the tropical variety, V plus trop of P, to be the collection of common positive tropical solutions. Okay, and so now I want to tell you about something a little bit simpler than the flag variety, but this was sort of motivation for what I was working on. Oh, I should have mentioned also that this idea of like positive tropical varieties comes from work of like Spires and Williams, probably worth knowing because I'm about to cite one of their results. So let pkn be the Plucker relations for k-planes in n space, and this is a subset of those polynomials I introduced, those relations I introduced way at the beginning, but you're kind of just looking at the relations between the top k by k minors instead of all the top minors who are restricting to minors with some fixed size. But anyways, it's some set of relations and they generate some ideal, the Plucker ideal. And we're going to define the tropical Grassmannian to be the tropical variety of that entire ideal, and the Dressian to be the tropical variety of the relations themselves. You know, with normal polynomials, these would be the same thing, but when you have these minimizations in the tropical world, things don't translate as nicely between the relations and the ideals they generate. So the tropical Grassmannian is actually strictly contained in the Dressian. It satisfies more relations and it is strictly contained in the Dressian. However, if we look at the positive parts of these varieties, so the positive tropical Grassmannian is the positive tropical variety of the entire ideal, and the positive Dressian is the positive tropical variety of just the Plucker relations, then we get that these two spaces are equal. The tropical Grassmannian equals the Dressian. The positive tropical Grassmannian equals the positive Dressian. Okay, so with that result in mind, I was looking to do something similar for the flag variety. So we're going to let the instance Plucker ideal be the ideal generated by these instance Plucker relations, which are these relations between the topmost minors of matrices. And the tropical complete flag variety is going to be the tropical ideal, the tropical variety of this entire ideal. And the complete flag Dressian is going to be the tropical variety of just the relations that generate this ideal. And again, we get a strict inclusion. The tropical flag variety is strictly included in the flag Dressian. But we can define the analogous positive version. So the positive tropical complete flag variety is going to be the positive tropicalization of the entire ideal. And the positive complete flag Dressian is going to be the positive tropicalization of the relations that generate this ideal. And if we do that, well, then we actually do find equality, just like in the case of the tropical Grassmannian, which is something I showed in a paper I'm working on. Yeah, so that's very nice because, oh, you know, maybe I should have mentioned that when I say these are not equal and they're strict containments, it's not like there's just a couple of points missing. Like they grow at different rates. Like one grows quadratically, I think, and one grows linearly, the size of the space. And so I just want to give a broad outline of the proof, because this is really going to tie together what I was talking about at the beginning with my parametrization of the non-negative complete flag variety and this tropical stuff. So here's the idea. There's a result from Pachter and Sternfeld that lets us take a surjective subtraction-free rational map from the positive real numbers onto the non-negative flag variety, and to turn that into a surjection from the real numbers onto the tropical flag variety. So the good news is I have such a map. It's this thing I was talking about the graphs earlier. So let's call that parametrization phi. And what I want to do is I want to construct some inverse psi to phi. And psi is only going to depend on the Plucker coordinates because it's a map from the flag variety back to the real numbers. So it's some function of the Plucker coordinates, which means I can apply it outside of the non-negative flag variety. I mean, it's an inverse on the non-negative flag variety, but I can apply it to other points, no problem. And then what I need to do is I need to show that trop of phi and trop of psi are inverses. So when I tropicalize, I maintain this property of being inverse. And then the key is that if Q is any point in the Dressian, well, I can write that Q is tropophi composed with tropopsi of Q, because this composition is just the identity. But tropophi is a surjection onto the non-negative tropical flag variety. So I conclude that Q is actually in the non-negative tropical flag variety. And that shows us that the Dressian is contained in the tropical flag variety, and that's the harder direction. The other direction is kind of obvious from the definition. And that shows us that the two spaces are equal. And that is what I want to tell you. Thank you very much.
Okay, thank you, Jonathan. Let's give him an applause. Okay, are there any questions for Jonathan?
What is the motivation behind the definition you gave of a positive solution to a tropical equation?
Yeah, that's a great question. There is another definition of a positive solution, which makes the notion of positive much more obvious. And that comes from looking at Puiseux series. And you're looking at ideals over the Puiseux series. And Puiseux series are like power series in rational powers of T. And the positive solutions are ones that come from Puiseux series, which have a positive leading coefficient, a real positive leading coefficient. And there is a way to draw that out, maybe kind of a little bit of a more intuitive reason that this is positive in like this language is that if I were to write this as P equals 0, what I could do is I can rearrange this as x squared plus y squared equals 3xy. So when I write everything with positive coefficients, one of my minima need to come from each side of the equation.
Okay, that makes sense. Thanks.
So is this stuff that you're studying connected to positroids?
Yeah, so there are definitely connections. Like so when you tropicalize, you could have some infinities. I didn't really mention that, but you're allowed to have infinity. It's like the tropical variety lives in the space R union infinity, or some number of copies of that. And if you look at the non-negative Grassmannian and you look at the support of a point in the non-negative Grassmannian, so those indices which are not infinite, that support is going to be a positroid. And so these are going to be flags of positroids. And they are flags of positroids that are representable. Like there's two notions of flags of positroids. You can take a bunch of positroids that are forming a flag, but don't have any necessarily interrelations between them. This is a stronger notion of quotient of positroids where they have to like somehow be simultaneously representable in a single matrix.
Okay, cool. And it's exactly that. It's not like they all are that and there's others. Like that is like
I'm not sure if it's exactly that.
okay.
I need to work through some of
I mean, I was wondering more like, is it that this fully, like every representable positroid would show up this way, or whether there's like, this just describes some of them.
So I want to be careful because I don't know the answer exactly, but
Okay,
every
yeah.
representable positroid shows up in the non-negative flag variety. And then I think when you tropicalize it, you get something with that same support. And that's kind of going to be a positive answer.
When you did this construction where you took a reduced word and you built this graph picture, is that a construction that's invariant under braid relations at all?
I'm not sure. It's a good question.
Any other questions? Okay, let's give Jonathan and the replies for great talk.